Okay, so I'm not sure if I wrote this the correct way on Monday or not. I remember saying 15, but I don't remember if I put it in the right place or not. So pKa's, they're important, but I don't really need anybody memorizing numbers. This is a number that we all know because it's been around quite a bit. Alcohols all have the same acidity, they all have the same pK of about 16. And we know that we can pop that H off. It's not acidic at that point, but it's doable. This is acidic. Carboxylic acids all have pKa's in the 4 point something range. 4.2, 4.8 is about normal, depending on if there any kind of electron withdrawal going here. So that's a real acid. This was something that we'd seen. Phenol had a pK of 10, and that has a trivial name of carbolic acid. So these alpha hydrogens, they should be actually pointing at the H, not at the carbon. These positions right here, those hydrogens, this is as acidic as an alcohol, but it just looks like it's part of the chain. This is more acidic than a phenol, but again, it just looks like it's part of the chain. So now we need to get used to the idea that yes, I can react at this because this is clearly a functional group. Yes, I can react there because that clearly is a functional group. But now there are other places in the molecule that the reaction can be occurring at that you also have to consider. It's never going to be here. Once you get to be aliphatic hydrogens, your pKa goes up into the 40s. They're off limits. You're not going to pull those off with base. So we know that enols exist. We know that enolates, same thing, just with the negative charge, exist. Let's use this to our advantage. So the following couple of mechanisms either use an enol or an enolate in their intermediate. So these are reactions that rely on enols or enolate intermediates. Okay. So if I take a ketone, I can replace one of those hydrogens that are alpha to the carbon. It's the positions that are alpha to the carbonyl that are going to be acidic. I can replace one of them. Let's be judicious with this. So I'm going to do a mono alpha halogenation. Like this. Only has alpha hydrogens on one side. If I had this be an aldehyde, I would also only have alpha hydrogens on one side. But it's a ketone. Those are my alpha hydrogens. They can be replaced. They're a little bit acidic. Got a pKa should be about here. It should be about 15. I'm going to put this in dilute acid, and I'm going to present it with some actual halogen. I'll give it a molecule of bromine. Bromine, turns out, is quite a nasty chemical. It's a liquid, it gives horrendous chemical burns. We have a giant bottle of it in the stockroom. I don't know why, because it's not something that I would trust to be in the general chemistry teaching lab. Really, really bad chemical burns from that. And I'm going to replace just one of those hydrogens. So the strategy for making this molecule look biggish and ugly at the beginning is actually for your benefit. There's no alpha hydrogens on this side of the molecule, therefore this side of the molecule is off limits. And unless these conditions are sorting out to be some kind of electrophilic aromatic substitution, then you're going to be dealing on that side. So let's look at the mechanism.
I'm sorry, can you say that again?
Well, if this said bromine on the top and then FeBr3, that would be a Lewis acid catalyst. That would remind me, hey, that's an electrophilic aromatic substitution. I'm going to be reacting at the ring. Okay. I don't have any of those conditions here, so this is reacting somewhere else, and it's going to react
at
right
the
here.
alpha.
Mm-hmm.
Okay.
Let's look at this mechanism. We could do this equally well. So things to exclude the left-hand side of the molecule from undergoing reaction. If I made the left-hand side of the molecule an aldehyde, well, it's not going to react at the aldehyde hydrogen. Or if I made it an alkyl group that had no alpha hydrogens. But either way, I'm going to make this kind of big and bulky and scary. There's nothing to be scared about when the molecules go cyclic. The purpose for the ring being there is that there are no alpha hydrogens on that side. Okay, that's all. That's all. Okay. Forming this in dilute acid. You should probably use sulfuric acid, phosphoric acid. Using the hydrochlorics, again, with the oxygen chemistry, is probably not the smartest idea. Okay, we've seen this before. Equilibrium arrows. No strong nucleophile. Only positive charges in my mechanism at this point. That oxygen just got protonated. Here's where you have to write the hydrogens in now. So usually by this point we're into writing stick figures. Now that you're thinking about reacting at a place other than the functional group, you need to write the hydrogens in. So sometimes writing stuff out the long way works to our advantage. This reaction is performed in dilute acid. So for every H+, there's going to be a large quantity of water. This is our nucleophile. This is our base. The reaction is being performed in acid, but here's the water behaving like a base. It's going to take that alpha hydrogen. It's not going to react at the carbonyl. Could it react at the carbonyl? Sure. Does it react at the carbonyl? Yeah. Nucleophilic addition of H+ and H2O to this makes a geminal diol. That's all in equilibrium. And if you pump it full of water, you'll make a geminal diol. But it's in equilibrium, it's going to come back to this. We're going to do something that shows you another possibility. I'm going to take these electrons. So I'm going to take the H, leave the electrons behind, take them and put them in a carbon-to-carbon bond. That carbon already had 4 bonds, but it has an alcohol built in right here, ready to go. So make the alcohol on the top. And I've got H3O plus right here. That is my enol, part alkene, part alcohol. So I've made the enol just by putting it in acid. Here's where the second part comes in. I'm going to bring in a halogen. And this is something that you've seen before. You've just not seen it this way. You've seen halogens interact with alkenes before. You saw that in organic 1. Alkene plus bromine does an electrophilic addition across that double bond. So a reminder would be, here's an alkene, let's make it asymmetrical so we can use a rule. You've seen this before. This is an adaptation of what you've seen. Big pi system, right here. And then the bromines have these enormous clouds of electrons, okay? And the frontier bromine interacts with that pi cloud, pushes its electrons, the big diffuse cloud of electrons, to the back, which means that the bromine at the back gets to be a little bit negative, and the bromine at the front gets to be a little bit positive. Oh, electrophile now. Area of electron density is your pi system in the alkene, it's nucleophile. And then here's your electrophile. And it reaches out and grabs it and adds that bromine to one of those carbons. Which one?
One with the R.
Not the one with the R. Because if you add the one with the R, then the plus has to go somewhere else. Remember, you have to leave a plus behind. You're going to make a carbocation. So the carbocation goes to the most substituted carbon in the alkene. Whose rule is that? It's Markovnikov's rule. And because the electrons dead-ended into that bromine is now a bromide. So you get the vicinal addition. And because bromines are really bloody enormous, you're going to get one in the top and one in the bottom. But because that molecule can rotate around this bond, there's no point in showing it. It only really reveals itself in planar molecules, cyclic molecules. Okay? So we've seen that reaction before. Let's just apply it to this. It's a little bit different. It's a little bit different. If this were just a regular alkene, both of those bromos would add. The first one is an electrophile, second one is a nucleophile. But this is not an alkene. This is an enol. And one of those carbons is not up for grabs. Not up for grabs. Because here's a pi system. Here's a diffuse cloud. Yes, we're going to induce a dipole by repelling these electrons to the back, exactly the same way that we did before. So this frontier one is going to be attacked by that pi cloud, and it is going to break the bond to a bromide, exactly the same, but make it be from the middle of the bond. But in order to do that, the molecule is going to make that happen by reforming this carbonyl. Which now the question of which one of these two carbons, left or right, left or right, which one of those two carbons gets the bromo? Can't be this one. Cannot be that one, because the carbonyl is reforming here, and this already has all of the bonds that it needs. The bromo has to go here. And that's it. We're only going to use one of them. A regular alkene does an electrophilic addition. You add both of them. First half is the same, but we're only going to see it once. There's the carbonyl. It's still protonated. Here's the rest of my molecule. And there's a bromo in there now. All we have to do is resolve that positive charge. What's missing from the sketch?
The other
The
bromide.
bromide. Okay.
So that's going to go in a
Here's a question, don't fall for it. Don't fall for this. I got a negative and a positive. Can I do this?
No,
No.
It's gonna
Why
go-
not?
because the oxygen has the positive charge.
Yeah, but I push the I push the electrons towards the positive and resolve that anyway. Why is it not this that's taking the H plus?
Because we're in acid.
It's actually going to be a molecule. It's most likely going to be a molecule of water that does it. I don't ask you to show all of those little details. Cannot be this. Cannot be that. Because that would make HBr. And what do we know about HBr? It's an acid. What kind of acid is it? It's a really strong one. And the definition of strong acids is that in solution, they're dissociated 100%. So the chance of that recombining with an H plus, 0. No chance at all. No chance. Don't be tempted to do it. Okay. But for full credit, you have to write, hey, I've lost a negative. Let's get rid of that. We're going to show that the acid is catalytic. It goes in the first step. It comes out in the last step. And I put a halogen into my molecule, which can be really useful. Because that's a really good leaving group now, especially bromo. Those are good leaving groups. Okay. Under those conditions, we're going to put one halogen into the molecule. Let me tell you that there is nothing incorrect about what we've written on the board. So why is it wrong? There is nothing incorrect about what I've written on the board. Every single step is correct. Why is it wrong?
Because we don't have anything protecting the
What was the word that we used to describe the special characteristic of the H that is alpha to a carbonyl and therefore partly enol some of the time? acidic, right? The alpha hydrogens are acidic. What conditions did I just run my reaction in?
That's it.
Isn't that kind of dumb? Shouldn't I have done it in base? Yeah. Guess what happens when you do it in base?
It's quicker.
They all go. Every alpha hydrogen in the molecule goes. They all get converted into something else. So if you put it in the presence of chlorine, they all get chlorinated. You put it in with bromine, they all get brominated. You put it in with iodine, they all get iodinated. All of them. Which tells us sometimes we don't want everything to be removed. I just want one leaving group. Can I just have one leaving group in my molecule, please, so I can do something kind of cool at that site? Yeah. So this is set up to be inefficient. You're replacing an acidic hydrogen in acid conditions on purpose. You are limiting this reaction in its scope. When we do this in base, it all goes wild. That's why I wrote down, the title for that was, it was a monohalogenation. If we do this in base, all alpha hydrogens are replaced by halogens, all of them. And there is a nice special reaction that shows this. So this would be a per-halogenation. Per means lots. So let's look at, give me the name of an asymmetric ketone. That's symmetrical. Asymmetric. Carbonyl. Some group on this side, some group on that side. That's your left, your right. Okay, that would be asymmetric. But 2-pentanone has a methyl, and I'm going to keep methyls back because they're a special case. So give me another one. Just make the chain one carbon longer and move the carbonyl. 3-hexanone. Again, we would normally be writing that as the little zigzag things at this point, but I need to show the hydrogens. I need to show that they are there. Okay, so this side's not the same as that side. If I put this in with base, give me the name of a base. Yeah, that'll do. Sodium hydroxide. And then chlorine. I get all of the alpha positions to go. I got alpha hydrogens here, and I got alpha hydrogens there. Alpha just corresponds to how many positions away from the carbonyl am I? How many positions away from my functional group? Alpha, beta, gamma, delta, epsilon, blah, blah, blah. Do you know what happens when Here's the functional group. It can be a carbonyl, or it can be an acid, or it can be an ester. What happens when the molecule's really, really, really long? Let's say it's more than 20 carbons long, 26 carbons long.
It would do more than that.
Because the alpha's here, and the beta's there, and the gamma's here. And then we run in, and nobody knows what the middle part of the Greek alphabet is. Right? It goes alpha, beta, gamma, delta, epsilon, lambda. And then there's a mu and a nu in the middle. And then what?
Okay.
There's an iota and a theta, but we don't know what order they're in. Anybody know what order they're in? What's at the end?
Zeta.
You go from the alpha to the omega, right? The end of the chain gets to be the omega. Guess what's one in? No, we start giving them numbers. 1, 2, and 3. What's in fish oil?
Omega.
The omega 3s, 3 steps back from the end of the chain. Yeah. Because the chains are so long, fatty acids are so long that we name the end of the chain.
Question.
Yeah.
How do we get 4 chlorines on that?
I got, let me amplify it. Oh, out of here, because I don't express how much of that I've got. I'm assuming that's in excess. Ooh. So I got a hydrogen here, and a hydrogen here, and a hydrogen here, and a hydrogen here.
Right.
And that's in excess. I'm allowed to use as much of that as I want.
Okay.
Unspecified. Unless I put a 1 in front of it, I'm not being held responsible for how much of it I'm using. If I want to limit you to a specific quantity of reagents, I would write in front of it 1 equivalent. And that means you're only allowed to use that much. Okay? If it doesn't say that, if it's unspecified, keep reacting it until the reaction stops.
So could you say when you have an alpha hydrogen on there, so you have 2 on each carbon, that you would replace the same amount with what you're reacting it with? Okay.
Yeah. And if this is a bromine, they all turn into bromines. If this is an iodine, they all turn into iodines. Here's a special case. I'm going to need the whole board.
That's why I got the windows too. I like your paint. Can you paint me more? I love that.
The iodoform is a reaction that does this. It doesn't have to be aromatic. But again, I'm using an aromatic system on the left-hand side of my molecule simply because it has no alpha hydrogens, not because the aromatic imbues any special kind of characteristic to this molecule. I take a methyl ketone. That's all it needs to be, a methyl ketone. And I put this in base and lots of iodine. I make the carboxylic acid. And that's impossible. Yeah, because we told you already that ketones cannot be oxidized. There is no oxidative pathway up from a ketone. We had to invent those 2 special reactions, the Baeyer-Villiger and the Svern oxidation, to show you that there is a way. But now there's another one. Plus we did one in class, in lab, we did the bleach oxidation. That's an oxidation of a methyl ketone as well. If I have a methyl ketone, I make the carboxylic acid. And the way that I make it is noteworthy. Okay, again, I'm only using this side because there is no alpha hydrogen there. Not for any other reason. Here's how this works. It's kind of long. It's like 6, 8, maybe 8 or 9 steps. You're gonna need to show the alpha hydrogens hanging loose because I'm about to take them with a base. Previously, we had protonated the oxygen to make the pi bond even more susceptible to nucleophilic attack. Now I'm just going to go for it. I'm going to use this hydroxide, and instead of reacting as a nucleophile at the carbon, it's going to react as a base at the alpha hydrogen. It's going to take that H as an H plus to make H2O right here. So those electrons that are in the carbon-hydrogen bond have to go somewhere. They're going to go into the pi system between the 2 carbons, but that carbon already has 4 bonds. This, straight arrow now. Strong nucleophile coming, strong base, making this happen. This looks like an enol, only it's negatively charged. So this isn't an enol. That's an enolate. Enol means part alkene, part alcohol. Ate means negatively charged on an oxygen, the same way that sulfate is a sulfur with some oxygens and a negative charge. Okay, here comes the iodine. What happens next should not be difficult for everybody to visualize because we've already done it. Only this time around, we don't have to reconcile that there's a positive charge on the oxygen after we're finished. When the carbonyl reforms, that pi bond reaches out, grabs hold of the iodine, breaks the iodine to iodine bond, releasing an iodide, and putting one halogen on the alpha position. So the iodide floats away. Okay? Tell me one thing about iodine that we should know.
It's not good at making bonds.
No, it's terrible at making bonds. It's actually really good. If we could build it in as a leaving group, we would keep it. That's one. Wasn't the thing I was looking for. Tell me something else.
It's huge.
It is. It's really, really big, which is why it's not very good at making bonds in the first place.
That's all I got.
Okay. Where is it on the periodic table?
Group 7.
7. What's going on in group 7?
They want to be by themselves. Oh, yeah.
That's 8.
Okay.
Are the elements in group 7 easily oxidized? How about reduced? Ooh. Oxidation is the loss of electrons, reduction is the gain of electrons. What would a chlorine do? Does it gain electrons or lose electrons? Gains them to go to Cl minus. It does that really easily, right? Pulls electrons towards itself in a phenomenon called, if it does that, pulls electrons towards itself and ionizes its electron affinity. If it does it within the scope of a covalent bond, it's called electronegativity. Iodine's at the bottom of group 7, near the bottom of group 7. So it's not nearly got the electronegative power of a fluorine or a chlorine, but it is pulling electrons away. And the pi system is pulling electrons away up into the oxygen. How do you think that makes that hydrogen right there feel? Atoms don't feel anything. Atoms have no feelings. More easily to come off as a proton. In science words, more acidic. It just became more acidic. Just became more acidic. You weakened the carbon to hydrogen bond by pulling electrons away from the carbon to some other place. Okay? So that's now more acidic. Oh, I have an unlimited amount of base to be followed by an unlimited amount of iodine. Make sure it goes to the bond. This reaction just got faster. Make an enolate. There's your new enolate. Bring in some more iodine. Go through the whole rigmarole again. Missing an H2O here. Okay? At this point, that hydrogen is feeling really acidic. It's the remaining alpha hydrogen on a carbon that is feeling electron withdrawal by resonance up into the carbonyl and by induction down into two separate halogens. So along comes another equivalent of base. Makes the enolate again. We're going to need some more iodine. And we're back the way that we came from. I did tell you I was going to need the whole board. Okay. This reaction at this point is going right here, is going very fast. So each step gets progressively easier. The removal of those hydrogens becomes more facile, easier to do, easier to achieve. And now I'm done. This is the per iodination. I've removed all of the alpha hydrogens and replaced them with iodines. I'm done. I'm done. I've still got lots and lots of base available though. This base no longer has any acidic hydrogens to remove. It's got no acids left to react with. What does it do next? No base, no acids to remove. So it can no longer be a base. What would you have it do next? We've put so much of it into solution that there's nothing left to neutralize. It has to still be there. That carbon is on the losing end of a polar bond. So it's not like we haven't seen this before. Ketones react with nucleophiles by nucleophilic addition. So let's just go ahead and do that. They make those geminal diols where you put both alcohols on the same carbon, right? Now, ketones react with nucleophiles by nucleophilic addition. Esters, amides, acyl chlorides, carboxylic acids react with nucleophiles by nucleophilic acyl substitution. The difference being that esters have a leaving group. Ketones don't have a leaving group because the carbon-to-carbon bond is too stable. It's too strong. But there's a side effect. Carbon-carbon bond is usually stable. We don't see very many examples in the book of us breaking carbon-to-carbon bonds. We don't see that many examples of us making new ones. That's why they're so noteworthy. Here, with all this electron withdrawal, that bond's polar. Polar enough to break. This is our first and only example. Well, the Bayer Villager has a carbon-carbon migration. We're actually going to break this bond. There's so much electron withdrawal there. When I reform that carbonyl, break that bond, oh, that's my carboxylic acid. That leaves Ci3 with a negative charge. And that negative charge reaches out and grabs hold of something. What have they got that's floating around? The base has to be delivered in water. So I've got some water here. Or, you know, at the end, we could actually have to neutralize this reaction as the very, very last step. But that is going to turn into CHI3. The CHI3 is called iodoform. In the same way, the CHCl3 is called chloroform. You've all heard of chloroform. When CHBr3 is called bromoform. Form is the old word for one carbon before we had meth. So this is iodoform, and iodoform is a yellow precipitate. So this reaction serves two purposes. This has now become a test, spot test. You can do it in a test tube. This is now a test for a methyl ketone. Back in the days before we had infrared spectrophotometers and NMR and mass spec and all of those instruments, we had to devise chemical methods to determine what the structure of the molecule were. And methyl ketones fall apart in base and iodine to make this bright yellow precipitate of iodoform. That's a test for a methyl ketone. But it is also a very handy way of turning ketones into carboxylic acids. Okay, what is next? What is next is we're going to take ketones and aldehydes, and we're going to put them in base. We're going to make an enolate, and then we're going to have them reach out to electrophiles of our choosing, ones with new carbons in them. So instead of this reaching out and grabbing hold of a halogen that's got a little tiny positive charge on it, we'll have this be a carbocation. And we're going to build new complicated carbons into our molecules. And the functional group stays intact. So we take a ketone and we react it in base with the carbocation, alkyl halide, a haloalkane of some description, and make a bigger, uglier ketone. That's useful. We'll do that Friday.